Hi, I'm Stefan, and my third year project is a Spinnaker demonstration of an actor-critic reinforcement learning agent. Spinnaker is a neuromorphic computing platform used to model and simulate biologically accurate spiking neural networks. The project has been implemented on a Spin3 board, which has 4 processing nodes, each with 18 cores, where 16 cores are used to support the application, each being able to simulate around 1,000 neurons. The motivation behind pursuing a biologically plausible model and using a platform such as Spinnaker is inspired by the discrepancy of several orders of magnitude in computational efficiency between neurobiology and electronics. The task that I chose is solving a commercially available video game called Super Meat Boy, in which the main character needs to jump on platforms across the level, avoiding obstacles in order to reach a goal. This task is similar to the grid world problem, which is a common test case for reinforcement learning. Similarly to the grid world, the agent can move in the 4 directions of the 2D level, with the addition of other elements such as gravity, inertia, and friction, which means that the actions of the agent do not always go as planned. In this image you can see the first level of the game, with a red square-shaped character in the bottom left corner, and the pink goal on the middle platform. The following is a loop video of how a human would play the level, with the character jumping across the platforms to reach the goal. The model that I built to solve the game is inspired by the actor-critic architecture, where the agent executes actions and the environment sends to both the agent and the critic the information regarding the resulting state. The critic then evaluates the results and modifies both the policy of the agent and its own internal information, and then the game is restarted. This counts as one learning episode, and the agent in the next episode will now use the policy learned and the signal given by the environment to execute new actions, change its behavior if previous ones have been modified, exploit rewarded actions, and explore new ones if mandated by the critic. This cycle is repeated, the agents acquire the policy and the critic optimizes it until the game is solved. The model involves 3 components: the environment, the agent, and the critic. The environment input is determined by a computer vision algorithm which detects the position of the goal and of the agent by using template matching, and then sends spikes to the corresponding state neurons. These state neurons are connected to actor neurons representing actions. When fired, they send their spikes to a receiver that decodes the activity and translates it into button presses. After the agent finishes executing the moves, the critic takes the input from the environment regarding the position of the character and determines whether the agent made progress compared to the previous learning episode. After its evaluation, the critic uses a series of spike injectors to alter the synaptic weights of the actions through a process called spike timing dependent plasticity, which is believed to be the basis of learning a memory in the brain. This process is dependent on the relative timing of the spikes of the pre- and post-synaptic neurons. If a presynaptic spike is followed shortly by a spike from a postsynaptic neuron, the weight of the connection is strengthened. Conversely, if the postsynaptic spike arrives before the presynaptic one, the weight of the connection is decreased. The greater the weight between a state neuron and an actor neuron, the greater the probability of that action being executed for a given step. Thus, the synaptic weights between the state and actor neurons encode the policy of the agent. This more detailed diagram of the system shows the layout of the connections between the populations of state and actor neurons. The population of state neurons is represented in blue, and the population of actor neurons is represented in yellow. Each neuron in the population has an index, and by receiving the list of neurons that fired, we can determine the actions that need to be executed. For example, if we receive spikes from neurons 0, 6, 8, and 12, we can decode that the agent needs to walk right at the first step, jump right at the second one, and then walk right at the third and fourth. With these techniques, no other data structure is used to store the information about the policy of the agent, which gives a biologically plausible model for how memory might work in the brain by using synaptic plasticity. This diagram recorded during a simulation of the first level of the game shows the synaptic weights of 2 possible actions, walking right versus jumping right, that the agent could take as its second move. We can see that over learning episodes, with a critic altering the synaptic weights, the optimal move emerges. The following is a video of the agent solving the first level of the game. To achieve this, the model requires an average of 9 to 10 learning episodes for a total of around 2 minutes and 6 seconds. It can converge to different solutions, as seen in this second video of it solving the same level. It can also solve more difficult challenges. In this sped up video of the model training, the character starts at the bottom left and needs to climb to the goal, avoiding saw blades that kill the player and bring it back to the start. To solve this level, the model required 25 learning episodes for a total of 7 minutes, and it produced the solution shown in the following video. Some of the challenges of this project were finding the right architecture that would efficiently communicate with the network live while it is running, and the lack of tools that could be used to simulate or speed up the game for training and testing. Future work would involve improving aspects of the critic, such as detecting unproductive moves or mapping recurring actions to a single neuron. There is also a great opportunity for connecting the model to hardware in order to solve real-world puzzles with the help of sensors and actuators. To sum up, this project presents a scalable and reliable model for reinforcement learning, its concepts and implementation possibly being able to be used to improve the development and biological accuracy of energy-efficient technologies such as robotic prosthetics or mobile robotics. Thank you for watching.